A 10-ton steel train hits the brake run at 70 miles per hour, but you don't hear any squealing or see any smoke. Nothing clamps down on the wheels, and nothing actually touches the car. Yet the entire machine slows down in a smooth and controlled motion. It feels like the train just drove into a wall made of nothing. How do you stop something that massive without ever touching it? The answer lives inside the physics of a metal fin and a set of magnets. But the part that surprises almost everyone is that these brakes actually work better when the power goes out. To understand why that is so remarkable, we need to look at how roller coasters used to stop, because the early solutions were exactly as rough as you would expect. In the beginning, stopping the train was a manual job for a person called a brakeman, who rode right on the car. This operator watched the track ahead and pulled a heavy lever at just the right moment to drag friction pads against the wheels. If his timing was off, or if the pads were wet from a morning rain, the passengers got a violent jolt. Every single stop wore those pads down a little more, much like rubbing an eraser across a piece of paper until there is nothing left to rub. Engineers eventually improved on that design by using what we call a fin brake, or a clamp brake. Instead of putting pads on the wheels, they bolted a flat steel fin to the underside of the train and placed hydraulic clamps on the track. These clamps wait for the fin to pass through and then squeeze it from both sides to create drag. This was more reliable and much more consistent, but it didn't solve the core problem of contact and friction. But here's the terrifying part. In a friction system, the more you need the brakes, the less they actually work. If a train is coming in too hot, the physics of heat can actually make the brakes slippery. Here is why engineers had to abandon friction entirely. Heat is the real enemy in this scenario. Every time those pads grip the metal fin, the kinetic energy of the moving train converts into raw heat. That is fine for a single stop, but a busy coaster runs dozens of cycles every hour of the day. The pads build up heat faster than they can release it into the air, and when they get hot enough, they simply stop gripping properly. Engineers call this brake fade, and it means the harder you push the brakes, the less they actually work. Rain adds another layer of trouble to the mix. Wet pads on a wet metal fin mean significantly less friction, which leads to much longer stopping distances. That gap between where the train is supposed to stop and where it actually stops is the kind of thing that keeps safety engineers awake at night. Because of those risks, engineers stopped asking how to make friction work better and started asking a completely different question. They wanted to know if a brake could work without ever touching the train at all. The answer didn't come from traditional mechanics, but from the world of physics and the way metal reacts to a magnetic field. Think of it this way before we get into the technical details. If you drop a strong magnet through a copper pipe, you would expect it to fall straight through, but it actually floats down slowly like it is moving through honey. Even though nothing is touching the magnet, the copper pipe and the metal are having a conversation using invisible fields. That conversation creates a physical force that resists the fall, and that same invisible interaction is exactly what stops a roller coaster. We need to look at how this system is actually built to understand the magic behind it. On the track, engineers mount long rows of permanent magnets made from a mix of neodymium, iron, and boron. These are often called NdFeB magnets for short, and they happen to be the strongest permanent magnets on Earth. On the underside of the train, they attach metal fins made from copper or aluminum. These specific metals are interesting because they don't stick to magnets, but they conduct electricity extremely well. Wait until you see the thermal footage of what happens to these fins. Even though nothing touches them, they are about to undergo a violent molecular transformation that turns motion into pure energy. Look at the gap between the magnet and the fin. When the train enters the brake zone, those copper fins slide right into the narrow gap between the magnets. Even though nothing touches, something happens inside the copper the very second it enters that magnetic field. Think of it like a person who hates being pushed and reacts by pushing back just as hard in the opposite direction. Copper does exactly that when it encounters a changing magnetic field. As the fin moves through the field, the shifting magnetic environment forces the electrons inside the copper to start moving. They flow in tight circular loops known as eddy currents, and these currents generate a magnetic field of their own. By a rule of physics called Lenz's law, that new field always points in a direction that opposes the motion. The fin is essentially trying to keep its magnetic environment from changing, so it pushes back against the forward motion of the train. That pushback is the braking force, and the clever part is that it requires no physical contact at all. The strength of this resistance isn't a fixed number because it scales directly with how fast the train is traveling. If the train is moving at high speeds, the magnetic field changes rapidly inside the fin, which creates powerful eddy currents and a massive braking force. As the train slows down, the field changes more slowly, the currents weaken, and the force naturally tapers off. The brake is entirely self-regulating and adjusts itself every fraction of a second without a computer ever giving an instruction. If you want to see where all that energy goes, you can point a thermal camera at the copper fins after a high-speed run. They actually glow on the screen because all that kinetic energy and speed converted into heat right inside the metal. While the fins get quite hot, the magnets stay cool, and the train slows down to a near stop in a smooth, controlled way. If you enjoy seeing the hidden logic behind these machines, hit the subscribe button right now. We take apart the complex world one mechanism at a time, and you won't want to miss our next breakdown.
But there is a limitation to this technology that people rarely talk about. At zero speed, eddy currents stop forming entirely because there is no motion to create a changing magnetic field. No motion means no induced currents, which results in exactly zero braking force from the magnets. The magnetic brake is brilliant at scrubbing off high speeds, but it is physically impossible for it to hold a train perfectly still. This creates a massive engineering paradox. If the magnets can't actually hold the train still, how does the ride keep two trains from colliding in the station? The answer is a 100-year-old backup system that is actually powered by gravity itself. This is why every magnetic braking system is paired with a friction backup for the final stop at the station. The magnets handle the heavy lifting by dropping the speed from 70 miles per hour down to a crawl, and then a traditional clamp brake steps in for the last few feet to pin the train in place. These are two separate systems with two different jobs, meaning there is no overlap in how they might fail. The track itself is divided into specific zones called block sections that each have their own set of magnetic brakes. Only one train is ever allowed inside a single block at a time to ensure total safety. Even if a train stops unexpectedly, the one following it will be caught by the previous zone's brakes before it can get close. This block system ensures the track acts as a physical safety net that doesn't rely on human reaction time. Now, here is the part that genuinely surprises most people when they look at the schematics. Most riders assume a total power failure would be the scariest possible scenario for a roller coaster. While cutting the electricity and losing the brakes makes sense for a lot of machines, these brakes run on permanent magnets. Neodymium magnets do not need a single watt of electricity to generate a field, so they stay active whether the park's power grid is running or not. In fact, if the power goes out, the ride actually becomes safer. It sounds impossible, but the system is rigged to fail into a state of total lockdown. Here is how engineers used a simple spring to outsmart a blackout. In fact, the friction backup brakes use what engineers call a power-to-open setup. A heavy-duty spring is constantly trying to push those brake clamps shut, and electricity is only used to fight that spring and hold them open during normal operation. The moment the power cuts out, the springs take over and the brakes slam closed automatically. The system is designed to fail toward a safe state rather than away from it, so an outage actually triggers the brakes instead of disabling them. On top of those physical layers, a monitoring system called SCADA watches every single zone on the track in real time. This system uses dual controllers that constantly cross-check each other's signals so that a single computer fault cannot cause a safety issue. Anti-rollback ratchets on the lift hill also prevent any backward movement if the chain stops. Every single layer of the ride assumes the one before it could fail, creating a massive stack of redundancies. While neodymium magnets do eventually degrade over time, the process is incredibly slow and takes decades rather than months. Engineers plan for this by using annual recertification cycles instead of the frequent pad replacements that friction systems require.
This makes the entire assembly one of the most reliable pieces of engineering in the park. The whole system relies on a copper fin that resists change and a magnet that stays on forever. This setup needs no friction, no wear, and zero electricity to keep 32 people safe at 70 miles per hour. If you want to see more of the hidden logic inside the machines you use every day, hit subscribe and share this with someone who thinks roller coasters are just for fun.